semiconductor industry. I've been an early inventor of test technologies. Some of you may have heard of self-test, scan design, those kind of technologies. Tom was kind of an early inventor in those kind of technologies. Spent did something around 3 decades at IBM or something like that. So both as an inventor himself, then as a manager, leader, many years and many contributions there. After a few years at IBM, continued with a design automation company that some of you may also have heard of, Synopsys. Been at Synopsys for a while and made some further contributions there. And is here today to share with us some truths or something we might not quite know about, or we might be surprised, we'll see. And there's one more, well, maybe we'll get also to learn a little bit of some other hobbies that you also pursue. So welcome, Tom, and thank you.
Thanks. If we could turn those lights down, that would be great if we would. Really, there's just one slide. This is the slide, and the rest of the 45 minutes I'm going to talk about Andre as a graduate student. Oh, that is not part of the deal? Oh, okay. Have to be careful. Anyhow, thanks for having me. It's a real pleasure. And what I'd like to talk to you is about another inconvenient truth, but basically some thoughts for the next decade. So, first of all, you certainly know Sir Arthur C. Clarke, Space Oddity 2001, etc. But let me look at his first and third law. First law, when a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. Well, I'm not taking claim to either distinguished or elderly, although I may start having some down payment on the elderly part. We are going to look at some technologies, and I'm going to try to talk to you about some of the shortcomings of the technology and see where they go. And then he had one other one that I think is worth looking at. Any sufficiently advanced technology is indistinguishable from magic. And conversely, any technology distinguishable from magic is insufficiently advanced. And you know, to some extent, that's true in our semiconductor industry. I mean, if we could push it a little bit more, I think collectively we would have, but in actual fact, it is as far as it can be. But I'll try to talk about some that I think are indistinguishable from magic, and then I will try to talk a little bit and try to give you an idea of some of the boundaries where we've been. So let's talk about the nanometer rush. And of course, the nanometer rush, I have to talk about Gordon Moore and Moore's law. So basically, Moore's law is the cost is 1x for the number of transistors, and as you go and you increase them, you essentially double the number of transistors and you pay the same amount. And one of the things that Moore talked about in addition to this is that he basically said, we have been selling silicon at about $8 billion an acre for years. And that, believe it or not, sounds really funny, but that price has been pretty much constant for what up until about 90 nanometer technology has been true. But that's basically the underpinnings of Moore's law. I'm going to be a little bit more demanding on what Moore's law is, because I really want to, not to denigrate Moore, but to, you know, to dislodge the idea that we're still traveling on Moore's law today. We are not, and I'll try to show you why we're not. Okay, let's take a look at the very, very early technology, 100 micron. This is the first Fairchild chip here. It was a set reset latch, and here we are at M0. That was the first time for beginning of scaling. And then as we move along, we go along and up to 250, it was the 22nd step, 130. The 23rd step is 32 nanometers, 24th step is down at 22 nanometers. So you can see the number of iterations, and we certainly have been going down that path. But we've spent, over the last 50 years, $600 billion of R&D investment to get from the 100 micron level to the 22nd iteration, which is the 45 nanometer technology. So quite a bit of money being invested in order to get there, and obviously we've gone past the 45 nanometer node, and that 600 billion has gone up. But just for entertainment, I think the semiconductor world, you know, I think it's great stuff, it's huge and all that stuff. How big do you think the semiconductor industry is? Well, you know, you got to have something to compare it to. If I told you, which is actually fact, this entire semiconductor industry is smaller than all of Walmart. It's shocking to believe, but that's absolutely true. Walmart in the year, in terms of annual sale, is larger than the semiconductor industry. So we ought to get a little bit humble here. I know we think really great that we're the big providers of all this stuff, but it's not the biggest industry in the world. There are others that are bigger. So anyhow, just to put it in perspective. Okay, let's look at the nanometer rush from 40,000 foot perspective. Here you go. You can see up there we got an ST microprocessor in 1996. Here we go in 2006, saving lots of money, going through this thing, a lot less money. There's the same microprocessor in 65 nanometer technology. So essentially we're going from 350 nanometer technology to 65 nanometer. So that's essentially 5 nodes that we transferred, which would be a 32x improvement in the transistor size. But actual fact, it's 32.5x. But since the processor in the 2006 was about 20% smaller, we essentially got a 39x improvement over that period. So essentially Moore's law was alive and well, and we're getting very close. But the thing to notice is this one down at the bottom. Look at that, both 5 watts, all the same. So we were able to hold that constant. And now, let's talk about what Moore's law really is in terms of its full breadth. First of all, from one technology node to the next technology node, the densities go from 1x to 2x. You double the number of transistors. Okay, everybody's got that. That's what should happen. Performance goes by 1.4, and that's what has happened. Essentially, the threshold voltage went down, the transistors got faster, and we essentially got a performance increase of 1.4x. The power stayed the same, 1x. In other words, they were flat. Because when you turn these things off, they were off. And the amount of power there was virtually 0. So as a result, the amount of power from one technology node to the next technology node is virtually constant. And now the really saving grace is down at the bottom is the cost. 1x to 0.5x. For the same number of transistors at the next technology node, you paid half the money. Or for the same number of transistors, you paid half the money. Hey, it sounds like a free ride. Let's ride this forever. Well, then comes this guy, Bob Denard. Now, who's Bob Denard? Some of you may, I'm sure most of you have heard of Moore's Law, but not many have heard about Bob Denard. Maybe if you're in the technology world, you may have heard of it. Bob Denard is famous for 2 things, and I mean really famous. Let's talk about his first contribution of note. I mean, sure he's had many, but the first contribution of note was a little tiny patent. I mean, you know, it wasn't a great patent. It just had 1 transistor in the patent. You know, so, you know, can't get excited. But fortunately, what it was the single transistor DRAM cell. That was his patent. So in 1968, Bob Denard was the guy who was responsible for that patent and brought IBM clearly a lot of money via that patent. Because he has 1 plaque in his office from the New York Bar Association saying more things were made from that patent than any other thing known to mankind. If you think about the number of DRAM cells, I think it's probably true. At least more things that we know of. I'm sure mold-wise we've probably made more mold cells, but we don't count those. Okay, so what about the second thing? The second thing was Bob Denard headed a team in CMOS scaling in IBM. And his work in this area was done well before 1974, but he was coerced by his fellow workers, said, you got to write a paper, we got to get this down and write it down. And so in 74, they wrote a paper. And basically, it is the fundamental paper that talks about scaling. You know, 1/s to do this and 1/s to do that. And this is how you go from node to node to do the things that we just saw in Moore's Law. So That was the paper that he wrote in 1974. However, one of the little graphs that was in this original paper is the graph that you see here. Well, basically, it's the I-off current. And if you look down in the lower left-hand portion, it says 10 to the minus 10 amps. I mean, that's pretty small, right? Not a big problem. And then the variable on the bottom is the threshold voltage. Well, essentially in this paper, what it said was, is that if you change the threshold voltage by 70 millimeters, 70 millivolts, not millivolts, you get an order of magnitude in the I-off current. But who cares amongst friends when it's 10 to the minus 10? Who cares, 10 to the minus 9? Well, sooner or later, that's a train coming at you at very exponential speed, and that's basically what's happening. So let's go, and there is the real problem. Take a look at the nanometer rush here. So here we are at 250 nanometers. One of the processors, and as we move along, you can see the process going 100 nanometers. You can read all those things. I don't need to read them for you. But basically, the performance is going up. The power is going to say, well, now the power is starting to move up. And now here we are at 90 nanometers. We've got a lot more transistors. Everything's going great. The performance is not going up as fast as we want. It went 3.4 to 3.8. But look at the power. It went from 33, 89 to 115 watts. So now we have a problem with power, and essentially that became the limit. So there's the performance, and there's where the power is going up. And now let's see what happens where we stand now at 90 nanometers. What we'd like to see is the density improve at each technology node by a factor of 2. In actual fact, it's going up by 1.5. Performance should be 1.4, right? And what it is almost flat. And if you look at it, you don't see any Intel chips in the microprocessors going at 20 gigahertz now. They're still in that same range that we saw at 90. The power, instead of being flat, is starting to go up by a factor of 2. And the cost is still the same, still going at half at every transition. So let's draw some conclusions from the technology node. Clearly 2 phases. Exponential down to 90 nanometers. That's basically the Moore's law. And after that, it's asymptotic. Then comes Bob Denard, say, hey guys, you got to pay me now or pay me later. When you start messing with that threshold voltage, the I-off current is going to start attacking it. So now the increased power density is in fact the issue. Leakage isn't negligible anymore. VDD and the threshold cannot scale any further. So the interconnect RLC makes everything worse. Flat declining performances is the result. And so essentially what we're talking about is caution, discontinuity ahead. So be careful where you place yourself in this technology map. Okay, what else is going on? Well, in order for everything to work just fine, the way things were is from technology node, the transistor cost should go down by half. So essentially it should cost you 50% less. And if you go below 130 nanometers, it was 50%. And that's where we were in the flat part of Moore's law. But now as we move past 90, you can see that the cost for transistor, even down to 22, is 97% of the last one, which means you're not getting the cost benefit that we originally had with Moore's law. So what I really want to get across is not to denigrate Moore. Moore was a great guy. I had the pleasure of meeting him. He certainly was a very innovative challenger from beginning with the Fairchild and then starting Intel and all this stuff. But essentially, the Moore's law thing seems to be living on way past where it really exists. The essential scaling of Moore's law is no longer in effect. The cost models are different, and things are really changing. So as a result of these increasing costs, the guys in the foundry are feeling like they're getting beaten up all the time. So I mean, it's because it's getting more and more expensive. So for the nanometer technology, here we go. There are more inefficiencies ahead, and the area isn't free anymore. If we take a look at these particular things from the ITRS roadmap, you see the Moore's law, 1, 2x, 4x. That's great in terms of capacity. But actual integration capacity is really been less, 1.6 to 3. Single exposure, for single exposure, now what is all that gobbledygook for those people? That means that essentially you're just going to expose the mask once with the array, and essentially want to look at the capability of the numerical aperture that we need in order to do a single exposure. At 65 nanometers, we need 0.9, 1.3 at 45, and at 32 nanometers, we need 1.8. Well, we essentially don't have a solution for that. Single exposure lithography, 65 nanometer was dry. In other words, we could expose it in through air. 45 nanometer, we're going through water. And 32 nanometer, if you were going to do single exposure, you have to have this thing called extreme ultraviolet. And essentially, 3 years ago, there were only 2 of these machines in the world. One in Leuven and one in upstate New York, in Albany, New York. And essentially this, for those, again, the way chips are made, they essentially expose them with a wavelength of light that's 193.5 nanometers long. So essentially this is the wavelength of light that you're exposing on these chips, and you're trying to do 20, 30 nanometer things wide. So essentially you have to play games of trying to sort of finesse the wavelength of light to go around certain shapes so you get the pattern you want on the top of the chip. It's a whole science into itself, and it's very mathematical intensive, and it's interesting stuff. But the difficulty now is that the wavelength is just too long, so that's why people want this extreme UV. Well, extreme UV is 13.5 nanometers length wavelength. Oh, it's very short. Oh, good, we can do some things. Unfortunately, if you get that spectrum scale, visible light, ultraviolet, and then get the extreme, guess who's sitting at 10 nanometers? X-ray. So now you've got a source of light that, for exposure, that is extremely, could cause problems. So you've got a very difficult environment with this extreme UV. Okay, so let's go forward. Sorry about and that's so. Now, what do we do if we can't get this extreme UV? And matter of fact, the extreme UVs are just coming online today. I mean, IBM, before they were sold all their semiconductor to global foundries, were just saying, well, at least the throughput looks like it can be close to what we expect with the extreme UV equipment that they get from the suppliers. But in actual fact, there's controversy of whether it is going to be fast enough. So what have the technology companies been doing, TSMC and the rest, in order to be able to print patterns? Well, what they've been doing is something called double patterning. So essentially, if you wanted to do 32 nanometer at half pitch, essentially this is what you want to get. There are lines that are that wide with spacing like that, and that's the metal pitch at that first level. So the way you go about it is you essentially apply 2 sets of patterns. 32 nanometer pitch is what you want, and what you do is you get this point here, that's the substrate stuff you put down. There's the pitch that you can expose. You expose it once there, wash it away, expose again there, wash it away. So essentially, you double the number of steps in the manufacturing environment. Well, when you double the number of steps in the manufacturing environment, that's why that curve of cost started to go, well, as you looked at it, went from left to right, started going up. And this is just double patterning, and actually today people are talking about having to do quadruple patterning. And let me see if we finish here. Now we've got our wires and we've got our 32 nanometer pitch with double patterning. Again, this is causing the foundry guys to, want to leave town because there's so much pressure on them to essentially get things at very economical rates, and it's just quite a difficult thing to do. So, where do we stand today? Well, we certainly are doing double patterning, but in order to get to the really lower ones that are talking about 14, 10 nanometers, they're talking about quadruple patterning. In other words, instead of doing what we did twice, they're doing it 4 times. But the difficulty is, it's very similar to a graph coloring problem. You can't have this one next to that one and that one next to that one. So all of a sudden, in terms of your wire placement problem, it has to spread things out in the chip. So essentially the chip area is going to start to increase for the same amount of transistors you had before. And as a result of having longer wires, as we talked about earlier, with longer wires you have longer Elmore delay, and the overall time to essentially, in terms of performance, is now being eaten up in the wires. And we had a discussion earlier today that not only that, as the wires get thinner, instead of acting like copper, even though they are copper, their resistivity increases and they act more like aluminum. So basically the Elmore delay, the RC time constant delay, is getting worse and worse. So essentially, even though the transistors themselves may be becoming faster, the overall performance ability is not tracking as we would like. Okay. One of the things that Intel has been doing is multiple supplies, and essentially where you get 82 by 21 power islands sitting here with standby VDD and all the things you have to do for powering and getting low power. And essentially each one of these is a microprocessor, and trying to control the leakage power in these processors. We're going to come back to this design later when we start talking about what we think are some of the importance for this inconvenient truth with respect to the process. But you have to do lots of things in order to minimize the power of these things. Otherwise, it says there are 21 different power islands on this one processor in order to control essentially that thing that Denard talked about in 1974, that is the current that goes through there. Well, I think you might rather be placing little bits here in some of the design here, because it's getting more and more difficult. So now, where's the inconvenient truth about all this? Well, the other inconvenient truth is again, here's the quote by Moore's Law, that we've sold the area on silicon wafers for about $1 billion an acre as long as I've been in the industry. And it still is pretty close to that same number. So the revenue grows only if the volume, that is the number of wafer, grows, and that regardless of the technology node you're at. So that's the only way the foundries can make money. They have to sell more wafers. The throughput has to increase, and if it doesn't increase, then they're not going to be making money. Now, the margins are going to be eroding because of this curve. So there's a tremendous amount of pressure on the foundries to try to make money given this somewhat hostile environment that they're in. Well, if that wasn't bad enough, there are some companies that are trying to put Moore's Law on their head and essentially saying, I don't want to double the number of transistors. I want the same number of transistors I had for the previous technology in this technology, but I want them at half the cost. And the company that was really famous for doing that was Nokia. And why was Nokia doing that? Well, the reason they were doing that is they wanted to attack the lower end of the phone market because of the emerging markets in both China and India. And essentially, they didn't want to have all the little apps that we have on the phones today. They wanted to be able to get lots of product out to lots of customers. So by putting this kind of requirement on the foundry, essentially what they were doing, in a de facto way, the foundry was not making as much money as they should, or they needed in order to be profitable. So every technology revenue shrinks if volume doesn't double, and that's essentially where we're at. Well, this sort of grim news, didn't it? It doesn't sound like a really up-speech talk. I should probably leave town right now, huh? let's talk about some fun stuff. Fibonacci numbers. Fibonacci was an Italian guy who got credit for this numbering sequence. And you can see that there's 0, 1, 1, 2, 3, 5. And essentially what you do is you take the two numbers before, add them together to get the next number. 2 and 3 to 5, 3 and 5 to 8, 5 and 8 to 13. And it goes on. Obviously it goes on. These numbers were known way in the BC time, Aristotle's kind of time. So they've been known for a long time. Fibonacci gets credit. His name gets associated with it. But what's strange about Fibonacci numbers? Well, they are strange numbers. I mean, they look like somebody just made up this little algorithm to add up numbers and you get numbers. But there are some funny things. Take a look at this snail. The snail goes along, and essentially the way it builds its shell is the chamber, the size of the two previous chambers is the size of the next chamber. And it keeps going. But snails are smart. Guess what they do when they get, in this case, the Fibonacci number 8, which is 21, I think it's on there. Someplace you see, yeah, Fibonacci number 8 is 21. Once it gets to that size, it stops growing. Why does it stop growing? Well, it turns out that if it tried to go further, the thickness of the shell would be insufficiently strong enough to house 21 plus 13, which would be 34, the volume of 34, and it would crack. So you say, okay, you got lucky. So you found a Fibonacci number in snails, you know, big deal. Well, there's some other Fibonacci numbers. Believe it or not, the number of petals on a daisy. Boy, this talk's going downhill quick, isn't it? I mean, this is not a technology talk, is it? Anyhow, how about the 34 petals? How about with sunflower seed? Yeah, the number of seeds in the middle of a sunflower are 89. Now, all of these things have come to limits. Snail comes to a limit, can't go past it. The daisies come to a limit, can't get more petals than that. Sunflowers can't get more seeds. And we can't expand faster with Moore's law. I mean, we're sort of coming up to these boundaries. What do? Well, why don't we follow what the daisies and the sunflower seeds do? They know what to do, how to expand. Yeah, they can get lots more of them and you can expand. Well, the same thing's true in the technology. So let's take a look at it. Scaling means more of the same. Not necessarily better, but just smaller until infinity. It's 7 nanometers. Scaling is like fossil fuel, the easiest way to go. Unfortunately, also like fossil fuel, it is not sustainable indefinitely. Nanometer scaling is like a single-story house in the Manhattan Midtown. More resilient and self-healing ahead to fight against nanometer chaos. So, what's the nanometer solution? Well, I go talk to a couple of my buddies. We have a little long discussion. And what is it? It's integration. And that is integration from 2D to 3D. And that way there we can start to get the kind of scaling that we need to do things that we have been accustomed to with Moore's law. So here's 2D to 3D, you know, a single dwelling here versus Taiwan 104 certainly can give you more scaling, more chips, if you will. Well, let's look at the chip version of this thing. Here's a stacked thing from ST Microelectronics, and take a look. You've got solder balls on top of layers of chips connected on top of chips, and the end result is now you're getting integration levels that are not possible to get by just doing scaling with respect to the silicon. And if you take a look at the interconnects on these things, they're just spectacular. And this isn't, you know, something that happened just today. This is what, 2007, 2008. So this stuff is happening. It's the topic, as Andre knows, in the testing community, there's a lot of effort looking at how to test these structures, because, for example, these through silicon vias are incredibly small, and being able to determine whether they're working correctly or not correctly is a real challenge. But it essentially allows you to be able to get the kind of integration levels that you were not able to get before. So if you look at the 3D, much easier to do digital and analog on different substrates. Smaller footprint, higher bandwidth, short global, shorter global interconnects, 3-tier, essentially going from 33%, 4-tier going to 50%. Essentially, if you go through these 4 tiers, the silicon area is L squared now for each, at least the stacked area. The footprint is 1 L squared divided by 4 because you divided the chip up. Let's go back. And the corner-to-corner distance for propagation is just would be L plus epsilon. And essentially now you've got all of these parameters in this new stacked environment are much easier to deal with and allow you to get the kind of integration that you're having difficulty to get within the semiconductor foundry. And here's the thing about back-to-back and face-to-face. So what they're doing now is taking the chips and putting them upside down like this, mating them to one another with these through silicon vias, and those are the things that look like the roots of somebody's tooth there to communicate in between one chip to another chip. And here's another example of one of the ones from ST Microelectronic. Again, you've got the solder bumps, you got the chip, and then other chips, and then solder balls that goes on a board. And essentially that's one chip, which is 45 digital function. There's active function on this one, which is has analog function. And the reason is that it's much easier to do analog in a larger technology, and then the digital in a smaller technology, because you can take advantage of some density, packaging together, and essentially you get the 3D integration that allows you to essentially get more volume. Now, here's a cross section again of the ST processor, and essentially there's 1056 copper pillars, as you see them sitting through there, and there's other through silicon vias, other balls, and then these balls, the package sits on there. And essentially, even in the cell phones, whether it's Samsung or Apple that you have in your pocket right now, have these kind of technologies in them now, because just doing it with a single layer of silicon is not possible. Okay, let's go back to this this thing that we talked about a little while ago. That is this Polaris Intel thing where we had all those 21 power islands and all those huge number of processors in parallel. And essentially, if you integrate the processors with cache next to them, hook them together such that you essentially get the memory sitting right next to it, again doing the face-to-back kind of integration that we talked about in the prior slide, you essentially get something which is more of more, needs to be more than more, and essentially gives you the capability of getting very high integration of these designs. And this is one way of taking advantage of the fact that we're not growing as fast as we used to be able to grow. Tests from one, once to many, always, etc. Essentially, you've got all these different packages. And now, essentially, and I won't go because it's sort of getting to the end of the afternoon, but basically there's self-testing techniques that we can use to essentially attack these different structures. But the 3D integration test once, test always, 100 billion channel is within our reach, but 100 million unused various aging software, we're going to be required to have some sort of self-test and some healing and some reconfiguration on our chips. And essentially 3D power thermal analysis, all this stuff is really can be done a lot easier from this 3D package point of view. For example, you take a look at this, partitioning up the chips like this, power, thermal, and this is sort of what we showed in the prior package, where you get these different levels like this, put them together, and essentially now you get integration levels that we wish we could do with the current semiconductor environment, but now do them in the 3D environment that we had before. So what's happened? Well, so we had more, and we have been going for 2x, approximately every 2 years. That is until we hit 90 nanometers. After 90 nanometers, what happened? all of a sudden we get, hey, Bob Denard said, hey, I told you so. You start to get a little bit further down that curve, the I-off current is really going to start to hurt you. And so, is Moore's law dead? No, but it is different. It can be different, and it is being different. From 35 nanometers, we're now going to an area where essentially we're going to high K metal gates, there's the 193 nanometer light to expose, where we're moving down and going into even more denser areas with the extreme UV. So Moore's law is not dead, it just happens to be different. So what is next? And that is going to daisies, like Fibonacci, but integrated. The ability to integrate and essentially do these 3D packages gives us the ability to essentially stay on the road, which will be different. And, you know, there's design and EDA, so if united we can stand that the true genius of our industry, that our industry can change, our union can be perfect, what we have already achieved gives us hope for what we can and must achieve. And that's basically, you know, that's how this industry has been going forward. But if we go back and look at Christopher Columbus, who was going and exploring something, one does not discover new lands without consenting to lose sight of the shore for a very long time. Andre Gide. And that's basically, it takes a big jump to go from the single planar transistor environment that we had to go to these 3D packaging and make it work. So that's sort of like losing sight of land and going forward. So stop thinking of watertight compartments. The third dimension will keep Moore's law alive and well longer than the first two dimensions, and EDA advances along with reconfigurable architectures with adaptive applications should provide us with the necessary resilience and self-testing, and that's where we hope to go. So, I hope I've sort of given you an idea of what's happened to Moore's law, why we've slowed down, where we're headed with integration in ways that we can now use packaging to help us get further and further ahead and along the map of the integration that Moore talked about in 1965. So with that, we got a bad slide there. So we got to have some rest time here. Can't talk about technology stuff all the time. Yeah, this is close to Camp Moore. Well, this is Camp Moore. So as Andre said, I like to do lots of photography, particularly northern lights. And just got back again from Hudson Bay. So that's my talk, and I hope you enjoyed it. Thank you.